Hello! Welcome to today's lesson on weight and the center of mass. In today's lesson, we will define weight as the force exerted on an object due to gravity. Moreover, we'll see how the concept of gravitational field strength will explain the intensity of this force at specific locations. Next, we'll introduce how to calculate the weight of an object. Finally, we'll then define the center of mass as the point within an object where its mass is evenly distributed. So far, you are familiar with the concept of gravity, the natural force that attracts objects towards the center of the Earth. Building on this familiarity with gravity, we can now delve deeper into the concepts of weight and center of mass. Understanding these will advance our grasp of how forces act on objects and how we perceive and measure their effects in physics. Let's get started. First, let's break down the concept of weight. Weight is a force exerted on an object due to gravity.
Right, so for example, I weigh 80 kilograms.
No, this is a common misconception. Kilograms measure mass, not weight. Weight, on the other hand, is measured in newtons, N. The confusion often arises because our mass gives us weight due to the gravitational pull exerted by the Earth. One way of thinking about this is that mass is the pure amount of stuff that an object has. In contrast, weight is the attractive force that all of that stuff experiences in a gravitational field. Accordingly, weight is what determines how heavy or light something feels. For instance, a large suitcase feels heavy because it's being pulled towards the center of the Earth by gravity. However, that same large suitcase would feel lighter on the Moon because the attractive force of gravity is weaker on the Moon. In physics terms, weight can be calculated using the formula weight equals mass times gravity. In this equation, W is the weight, measured in newtons, M is the mass of the object in kilograms, G is the gravitational field strength. There are a few things to note about this equation. First, G is approximately 9.8 meters per second squared on the surface of the Earth. This means that every object accelerates towards the center of the Earth at 9.8 meters per second squared. Accordingly, an object with a mass of 1 kilogram has a weight of 9.8 newtons on Earth and exerts this force downward on the surface of the planet. With this explained, we can see that this equation, W equals mg, is practically identical to Newton's second law of motion, which states F equals ma. Specifically, we're calculating the force caused by gravity, and to do this, we multiply an object's mass by the acceleration caused by gravity. Another thing to note is that the value for g isn't the same everywhere. As we've alluded to, different locations have different gravitational field strengths, meaning an object's weight can vary based on its location. For example, on the Moon, the gravitational field strength is about 1/6 of that on Earth, so you would weigh much less there. To further understand this, imagine you are on a Newtonian weighing scale on Earth. If your mass is 60 kilograms, the scale reads your weight as approximately 588 newtons, 60 kg times 9.8 meters per second squared. If you took this same scale to the Moon, it would show a significantly smaller number because the Moon's gravity is weaker. Weight is directly proportional to mass. This means that if you increase the mass of an object, its weight increases at the same rate, and vice versa. For instance, a heavier object like a brick will exert a greater gravitational force than a lighter object like a pencil. Now let's explore the concept of the center of mass. The center of mass is the point within an object where its mass is evenly distributed in all directions. It's as if all the weight of an object acts at this one point, simplifying our understanding of how gravitational forces affect the object. Think about when you balance a ruler on your finger. To do this successfully, you need to find the ruler's center of mass. When the center of mass is directly above your finger, the ruler is balanced because its mass is evenly distributed on both sides. This concept helps us understand stability and balance in objects. For instance, if you have a rectangular piece of cardboard, you'd find its center of mass roughly in the middle. But if you cut an irregular shape out of it, the center of mass would shift. Understanding the center of mass is practical in many real-life situations. For instance, in sports, a gymnast must control their center of mass to perform flips and landings successfully. The same applies to designing stable structures, cars, and even everyday objects like chairs and tables. Let's apply what we've learned to a few specific problems to consolidate our new knowledge. Problem 1. calculating the weight of a backpack on Earth. Firstly, identify the mass of the backpack. Suppose the backpack has a mass of 5 kilograms. Next, use the formula for weight. Weight equals mass times gravitational acceleration. Then substitute the values. Weight equals 5 kilograms multiplied by 9.8 meters per second squared. This gives us 49 newtons. So the backpack weighs 49 newtons on the surface of the Earth. Let's look at another problem, calculating the weight of a laptop on the moon. First, we need to identify the mass of the laptop. Suppose the laptop has a mass of 1.5 kilograms. Note the gravitational acceleration on the moon. Gravitational acceleration on the moon is approximately 1.63 meters per second squared. Next, use the formula for weight. Weight equals mass times gravitational acceleration. Then, substitute the values in. Weight equals 1.5 kilograms multiplied by 1.63 meters per second squared. This gives us 2.445 newtons. So, the laptop weighs approximately 2.445 newtons on the surface of the moon. Let's go through one last problem, comparing weight on Earth and Mars. First, identify the mass of an object, let's say a rock. Suppose the rock has a mass of 10 kilograms. Note the gravitational acceleration on Earth and Mars. Gravitational acceleration on Earth is 9.8 meters per second squared. The gravitational acceleration on Mars is approximately 3.71 meters per second squared. Next, calculate the weight of the rock on Earth. Weight on Earth equals mass times gravitational acceleration. Weight equals 10 kilograms multiplied by 9.8 meters per second squared. This gives us 98 newtons. Now calculate the weight of the rock on Mars. Weight on Mars equals mass times gravitational acceleration. This is 10 kilograms times 3.71 meters per second squared, which equals 37.1 newtons. So the rock weighs 98 N on Earth and 37.1 newtons on Mars. By working through these examples, we've observed how to apply the equation W equals mg to calculate the weight of objects with different masses and in different gravitational fields. This process helps us understand how changing either the mass or the gravitational acceleration affects the weight of an object. In this lesson, we've dived into two fundamental concepts in physics: weight and center of mass. Weight is the gravitational force exerted on an object, measured in newtons, and it can vary depending on the location's gravitational field strength. The center of mass is the point where an object's mass is evenly distributed, simplifying how we perceive and measure stability and balance. We also looked at how to apply the equation W equals mg to calculate the weight of objects with different masses and in different gravitational fields. By grasping these concepts, you enhance your understanding of how forces act on objects and how we interact with the physical world around us. Whether you're calculating your weight or balancing objects, these principles are foundational in the study of physics. Watch the rest of the GCSE physics course at Sophos Education.